All right, here we go. Unit 3, Day 3. It's going to be an overview of multiple factoring methods to find solutions. So we spent a couple days reviewing factoring trinomials. Today we're going to wrap that all together and talk about a couple of other special cases that you might see. So a few key points from last class to remember. Number one, the whole reason we factor, the whole reason we do this is to make it easier to find solutions to equations. So solutions, just what could I plug in for the variables to make this a true statement? We have a special type of solution if one side of the equation is set equal to 0. We call those solutions zeros. And if we were to graph those zeros, those would be the x-intercepts because they would be the values of x that give you out an equal 0 for y. And the whole reason we factor, like I said, is to make it easier to see what values of x I could plug in to make my expression equal to 0 due to what we call the zero product property. Remember, the zero product property is just anything times 0 equals 0. So if you can find a way to make any of the factors 0, the whole expression will be 0. So let's see a quick review example here. Find the x-intercepts. So find the values of x that make y 0. Find the zeros of the function y equals 2x squared minus x minus 15. So the x-intercepts can be found where y equals 0. So the first thing I'm going to do is I'm just going to rewrite this. 0 equals 2x squared minus x minus 15. And I could stare at this for a while. I could just start plugging in, 3, maybe 4, some negative numbers. It's really hard to just look at this and think about what values of x would make this a true statement. Factoring is what allows us to make this easier to see. Factoring this trinomial step by step, the first thing I know is that to make this 2x squared, 2 is a prime number, so there's only one way this can be done, 2x and x. And factoring is it's something that takes practice. It's something that takes going through and getting quick with your mental math. I could, if I needed to, I could go all the way through. I could say 1 and 15. Then I could try 15 and 1. Then I could try 3 times 5. And I could try 5 times 3. And it's just a matter of going through these combinations until you can see which one will give us a middle term of negative 1x. And so I need two numbers that multiply to make negative 15. They multiply to make a negative, so one's going to be positive and one's going to be negative. And when we make the middle terms are different by 1x. And so I'm going to show you how I think about this. I like to do it without even thinking about the signs first. So let's see, first let's say I try 3 and 5. I think about what the middle terms would be. I'd have a 3x from that part of my distribution, and I'd have a 10x. Well, there's no way I can make a negative 1x through any kind of combination of 3 and 10x. So I go back to the drawing board. I say, okay, maybe it's the other way around. Let me try 5 and 3. So I think about, okay, what would happen here? 5 times x would be 5x. 2x times 3 would be 6x. I can make a negative 1x out of that as long as the 6 is the one that's negative. So if I need the 6 to be negative, I need this to be a minus 3, so that negative 3 times 2x is negative 6x, and so my other one must be plus 5. And so just to check, I'll go ahead and do all of the multiplications here. 2x times x is 2x squared, 5 times x plus 5x, 2x times negative 3, negative 6x, and 5 times negative 3, negative 15. So we'd put all these together and we'd have 2x squared minus x minus 15. So check. So this is our correct factorization. Now, the reason this factoring makes life easier is because of the zero product property. That tells us that if either let me do this in gold, if either the left parenthesis 2x plus 5 equals 0, or the right parenthesis, x minus 3, if either of these things is equal to 0, because anything times 0 is 0, the whole expression is 0. So I just solve these. X minus 3 is 0. Well, adding 3 to both sides, x equals 3 is one of the zeros. Sorry, this should say zeros here. Is one of the zeros. It's a solution to 0 equals 2x squared minus x minus 15. The other one just takes one additional step. We would subtract 5 from both sides. We'd have 2x equals negative 5, and we'd divide by 2 to get x equals negative 2.5. So these are the two values of x that if I plugged them in, because of the zero product property, one of these parentheses would be 0, the whole thing would be 0, and factoring tells us this is the same as the original equation. So it's what would make our original function equal to 0 as well. And so I can see on the graph here that this is correct. Here is 1. When x is negative 2.5, y is 0. That's one of the x-intercepts. And as well, when x is 3, y is 0. So those are our two y-intercepts. They are our zeros, our solutions to the equation. So that's a review of what we did last time. Let's talk about just 3 quick extensions to this idea. Extension number 1. The whole thing here rests on using the zero product property. So one extension is solving an equation that isn't already set equal to 0. The whole point of factoring is to be able to use the zero product property to find solutions. If your equation isn't already set equal to 0, you can often rearrange it and then use these same techniques. So if I'm asked to solve the equation x squared minus 12x plus 21 equals negative 6, again, what I'm being asked to find is what could I plug in for x to make this true? So I could just keep trying random numbers, plugging in for x and seeing when I get negative 6 on the left-hand side. Or I can use inverse operations to make sure that my leading coefficient is positive and my equation is set equal to 0. So the only thing I would have to do for this one is add 6 to both sides. Because if I do that, what I would have here is x squared minus 12x plus 27 equals 0. And since it's now set equal to 0, I can factor this to find the solutions more easily. This is a trinomial where a equals 1, so we would have x and x. This is my favorite type of factoring, when the c term is positive, but the b term is negative. So we need two numbers that multiply to make a negative number, that multiply to make a positive number, but add together to make a negative number. The only way that's possible is if it's a negative times a negative to make a positive. So these both have to be negatives, and it turns out this is going to be negative 9 times negative 3. And just to check, x squared minus 3x minus 9x plus 27. So that checks out. We have now a much easier equation to solve for. Those parentheses are much more easy to look at and identify the solutions via the zero product property. One solution is when x minus 9 equals 0, which will just be when x equals 9. The other solution will be x minus 3 is 0, which is when x is equal to 3. So those are the two solutions to our original equation. Let's just kind of check one just to see the idea here. The idea is that if I plug in a 3 for these x values, this would be a true statement. 3 squared is 9. Negative 12 times 3 is 36. So we would have 9 minus 36. That's negative 27. Plus 21. That is equal to negative 6. So that does check out when we do that math. So that does check out for us there. And it would also check out for 9. All right, 2 more quick extensions. Extension number 2, factoring out a greatest common factor. So sometimes we can use this same idea, not just with quadratics, with things with a leading term with degree 2, a squared term, but when we have a cubic function as well. And the reason we can do this is because all three of these terms share a greatest common factor that we can take out. They're all even numbers, 2, 16, and 30. So I can factor out a 2, and they all have at least one x. So I can factor out a 2x. What factoring out means, remember, it's saying, what could I divide each of these terms by, right? What could I divide each of these terms by? And so if I multiplied this back out, I would have the original expression. Well, 2x times x squared would be 2x to the third, so that works. 2x times negative 8x would be negative 16x squared, and 2x times plus 15x would be 30x. And now I can factor my trinomial. So the 2x stays how it is, but I'm going to take this bigger parenthesis and break it up. This will be x minus 3 times x minus 5, right? Two numbers, they multiply to make negative, sorry, that should be a negative 15, not a 15x there. They multiply to make negative or positive 15 and add together to make negative 8. Now we can use the zero product property again to find solutions. The two that we know how to do really well now, one would be that x equals 5, one would be, x equals 3, one would be that x equals 5. The one that is very easy to forget is this leading factor, because it is also something that if it was 0, the entire expression would be 0. When is 2x equal to 0? Well, when x is equal to 0. So our three solutions to this equation are x equals 0, x equals 3, and x equals 5. So that's extension number 2. Sometimes you need to factor out a greatest common factor. Final extension here today is something that hopefully you've seen before, the difference of perfect squares. So when two perfect squares are subtracted, it's like a special case of trinomial factoring where the middle terms have canceled out. And so I'll show you what I mean by this in a second. If we have x squared minus 21, it looks like there's a missing middle term. The reason there's a missing middle term is what's happening here is you wind up with x squared plus 0x minus 121. And so what you need two numbers that multiply to make negative 121 and add together to make 0. Well, if two numbers add together to make 0, they must be the same exact number, one being positive, one being negative. And it turns out that the way you factor this is x plus 11 times x minus 11. So you can see what happens. This would be x squared plus 11x minus 11x minus 121. These middle terms will cancel. And this is a special case that only happens, when you have the same number, positive and negative, which gives us a perfect square. So 121 is a perfect square because it's 11 times 11, right? This is why we call it a square, because it's like a square, 11 times 11. X squared is a perfect square because it's x times x to make x squared. Whenever you have one perfect square minus another one, subtraction, we call that the difference. This is called the difference of two squares. And you can factor it. The easiest way when you're getting started with this, until you have it just kind of like memorized in your head, is to pretend that the middle term is 0. Last thing for today, this can get a little bit trickier if you have to use some serious exponent rules and it's not immediately obvious that this is the difference of two squares. It turns out, though, that it is. If I look at 144 y to the 6th, or y to the 4th, using exponent rules, this is a perfect square because it's 12y squared times 12y squared. Exponent rules, we would add those exponents because this is 12 times y times 12 times y times y, 144 y to the 4th. So 144 y to the 4th is a perfect square. So is x to the 6th. because x to the sixth is just x to the third times x to the third. You would have 6x's being multiplied. This is also a perfect square. So this is one where you have to really have the difference of squares memorized. You can factor this as 12y squared plus x to the third times 12y squared minus x to the third. And we would work all this out. This would be 144y to the fourth, okay, starting to check out, minus 12y squared x to the third, plus 12y squared x to the third. See, once again, these middle terms will cancel, minus x to the sixth. There is our minus x to the sixth. And so if we wanted to factor, one other way we could come up with is the difference of squares. So those are just the various factoring techniques that you will encounter today. These are factoring techniques that are going to come up again and again and again and again. So there's going to be a good amount of practice with delta math. I'm going to let you